Today we're going to do mole-to-mole limiting reactant problems. When chemists work in a lab, they rarely carry out a reaction with exactly the amount of reactant that's needed for the reaction. I like to think about this in terms of baking. If I'm baking cookies, when I open up my fridge and pantry, I have the ingredients that the recipe calls for. Some of those ingredients, probably the majority of them, I have in excess. I have leftover or extra flour, more than what it calls for. But for example, if I'm making chocolate chip cookies, I may have just enough chocolate chip cookies for the recipe, or maybe I have less than what it calls for. And so those chocolate chips would be my limiting ingredient. In chemistry, we talk about it as a limiting reactant. It limits the amount of product that can be formed. And so in a chemical reaction, you can also have an excess reactant. This is the substance that is not completely used up in a chemical reaction. And so when we've been doing the problems up to this point, we've given you the limiting reactant. We've been basing our calculations off the limiting reactant. And many of the problems say that you have one of the reactants in excess. So I have a picture here of a reaction that I carried out with a copper solution and a piece of iron. And so if we look, this is at the end. We have a yellow solution and a red solid. So at the end of the video, we'll talk about what was in the solution, what was in the what's in our final solution, what is that red solid. So our problem is if we have 0.020 moles of copper 2 sulfate reacting with 0.081 moles of iron, what is the limiting reactant? What is the excess reactant? What is the theoretical yield of copper in moles? What is the amount in excess in moles? So there are quite a few problems in here, and we'll tackle them one at a time. So when doing a limiting reactant problem, I like to think about it in terms of what do I have and what do I need? So first, I know that I have 0.020 moles of copper 2 sulfate. I have 0.081 moles of iron. So and we have to have these amounts in moles when we're talking about what we have. Then I can think about, well, what do I need? So if I have this much copper 2 sulfate, how much iron do I need? So we're going to do a have to need calculation. And this is just a mole-to-mole conversion. I have 0.020 moles of copper 2 sulfate. I can convert from how many moles of copper 2 sulfate I have to how many moles of iron I need. And I just use the mole ratio from the balanced chemical equation. For every 2 moles of iron, I need 3 moles of copper 2 sulfate. And so I would multiply across the top of my railroad tracks, multiply along the bottom of my railroad tracks, divide. Remember sig figs. And so I would need 0.013 moles of iron. And then I would do the same thing over here. If I have this much iron, how much copper 2 sulfate do I need? And again, it's a mole to mole ratio. So I would write down what I have, convert from moles of iron to moles of copper 2 sulfate. And so for every 3 moles of copper 2 sulfate, I need 2 moles of iron. Multiply across the top of my railroad tracks, multiply along the bottom. I would need 0.12 moles of copper 2 sulfate. And so this is where I would compare what I have with what I need. Just like if you were baking and you were making a list of what ingredients you would have, you would compare what you have on hand already to what you need. So I'm going to subtract what I have minus what I need. And so if I have 0.020 moles of copper 2 sulfate and I need 0.12 moles, I am not going to have enough. 0.10 moles. I'm minus 0.10 moles of copper 2 sulfate. Over here, if I subtract what I have for iron to what I need, I would actually have an excess. I would have 0.068 moles of iron in excess. And this answers it answers 2 of our questions. We know that the excess reactant is iron. We know that the limiting reactant then is copper 2 sulfate because I don't have enough copper 2 sulfate. And then we know the amount in excess in moles is 0.068 moles of iron. So if we go back to our picture here, this yellow solution is an iron solution. It's the iron 3 sulfate that's in our equation. The red solid is copper. So initially I had a blue solution, I had a silver piece of iron, I let them react, and you can see we have excess iron in the solution. We'd have formed solid copper, and we want to know what our theoretical yield of the copper is. I could do this with a calculation. And so theoretical yield is always based on the limiting reactant. So I'm going to give you a definition for theoretical yield, and then we'll do the calculation. So you calculate from the limiting reactant. The theoretical yield is the maximum amount of product that can be produced for a given reaction. And so theoretical yield can also be called the calculated amount. This is not the same as what you actually produce. You can see in my beaker, I've actually produced copper, and we'll talk about actual yield tomorrow. So this is theoretically the amount of product you should form if the reaction goes to completion, if you don't have any contamination, if you don't lose any product. This is what you should theoretically produce. So we're going to go back up to our equation before we do the calculation. We are going to do the the calculation based on the limiting reactant, and that is the copper 2 sulfate. So we have 0.20 moles of copper 2 sulfate. We're going to use that to convert to how many moles of copper are produced. And so if we go back up to our balanced equation, this is a mole to mole conversion. I'm converting from moles of copper 2 sulfate to moles of copper. So if I go back up to my balanced chemical equation, I have 3 moles of copper 2 sulfate will produce 3 moles of copper. So we would have a theoretical yield of 0.020 moles of copper. And so if I go back up to our questions, we can answer our last question, 0.020 moles of copper. So we've gone over limiting reactant, excess reactant, theoretical yield. I would make sure you know those definitions. And then we've gone through the process of looking at what we have and comparing it to what we need to determine our limiting reactant and our excess reactant.